Ball bearings are really good at supporting rotating shafts while minimizing friction. They will fail, but we don't know exactly when, because failure is a random process. In other words, seemingly identical ball bearings will fail at different times due to external factors or different tiny structural and usually invisible internal weaknesses. We can represent all these factors with the random hand of failure. Beneath our hand, the time to failure represents the age of our ball bearing, which is measured in terms of the number of cycles it rotates, or revolutions. And the random hand of failure represents these factors that introduce uncertainty into the failure process. But just because something is random doesn't mean it's unpredictable. Let's say we observe 100 ball bearings failing. We can use a histogram like this to represent the density of their times to failure. In histograms, taller bars correspond to a higher number of observed times to failure at that point in time or usage. The histogram for 100 bearing times to failure is quite rough and jagged. But if we observe the failures of an incredible number of ball bearings, we will eventually get a smooth shape like this. We could call this shape an ultimate histogram because the bars are so thin that we can't see them. Of course, this can never really happen because we can never observe this many ball bearings until they fail. But this ultimate histogram leads us to another very useful concept, which is the probability density curve that forms the smooth top edge of the ultimate histogram shape. The probability density curve contains the same information as a reliability curve, as both curves describe the same random process. So